Hello everyone, my name is Aditi Yadav and today in this video I'll be explaining my machine learning final project which is taxi fare prediction system. So let's jump straight into it. The main objective of our project is to actually build an end-to-end taxi fare prediction system that can accurately predict fares whenever input features such as pickup, drop location, distance, time of the day are given. So the whole system is an end-to-end big data pipeline which takes in a large number of data sets and actually does all of the data engineering, and then we do the MLOps and finally be able to predict the input fare against the test data. So we'll look at the entire big data pipeline. Now the existing systems in place use performance metrics like MSE, but we'll use all the performance metrics like R square, root mean squared error, etc. We'll also be considering a bigger volume of data close to 100 GB. So basically that's the difference between ours and the existing systems in place. Now let's talk a little bit about the data engineering part, where we are actually collecting the data and doing all of the data engineering initially. So we basically have the TLC trip record data which is collected from the government side, which looks like this. Here if you see, the New York trip data is organized from 2009 till 2024, and each year basically has all the months from January till December, and everything is in Parquet format. So when we actually consider all of the data from 2009 all the way to 2024, it's easily over 75 GB of data. So we see that it has both variety and volume. Now let's coming to the raw data, that how does it look like. Here. So this is how a typical raw data format looks like, which is in Parquet format. Here there is a vendor ID, pickup date, time, passenger count, trip distance, etc. But the problem with this is we don't need all of these fields. We just need some of them. So that's why we have to do the initial data engineering part. Now let's look how it actually works. So let's deep dive a little bit into the data engineering part. So we basically collect the taxi trip data, which I just showed you in the New York TLC trip record, where we have the data stored from 2009 to 2024 Parquet format, which is raw format. So what we do is the very first step is to dump all of this raw data into our S3 bucket using AWS S3 and SDK client. So that is the data storage part. So once we have all of the raw data in S3, what we have to do is we have to basically clean the data. And in order to clean the data, we do two types of cleaning. One is we basically take in columns or the information that we actually need, which is reasonable for us. So that's what we do. And the second is we have to convert the Parquet format to the CSV format. As a CSV has good support for Python libraries and visualization, which we can actually use for cleaning analysis. So this is the transformation and the cleaning part that we do. In order to achieve this, we use PySpark. The PySpark we know is a distributed data cleansing and transformation tool which does parallel processing really well. So that's why I chose PySpark, and in order to basically orchestrate the movement from PySpark to S3 and again S3 to PySpark, we use Node.js, which acts like a backend server or an orchestration tool. So there are other similar tools also like Airflow, but that was actually taking time, and Node.js is lightweight and easy to set up, so that's the reason why I chose Node.js. Now once we have the final clean data in our S3, we basically take this initial clean data and start the MLOps. So in MLOps we use Google Colab as an environment. So we read all of the clean data from the S3 bucket, and since the data set is large, obviously we cannot read all the data at once. So in order to do it in distributed manner, we use Dask. Dask creates the partitions internally and does parallel processing. we basically do the initial cleaning and outlier detection. So this is our EDA. So we do like missing value analysis, removing outliers, type conversion, etc. So we'll be seeing all this later in detail. And once we have the final clean data ready for training, we split it into training and test data. Then we train the dataset using random forest, like random forest algorithm, linear regression, and other algorithms such as gradient boosting, etc. Then we evaluate the model using the performance metrics such as root mean squared error and R square value. And then based on the performance metric, we select the best model. And then once we have the best model in place, we may finally make the predictions using the test data. So basically that's the high level flow that we have for our taxi fare prediction system, but we'll look at each one of them in detail now. uh, so so the very first step, as I mentioned, is we send the raw data to the S3. So this is how the initial S3 bucket looks like, where we have the raw data dumped into the S3 bucket here, as you can see. It's completely in Parquet format. Let's come back. Yeah, so where we have the raw data dumped into the S3 bucket and using of course the AWS S3 client, and then this is how the clean data looks like here. So everything is in CSV format and the data is clean. So this is our second S3 bucket once we have the initial clean data back to the S3 bucket in the CSV format. Now, so let's jump into the Google Cloud, in the Google Colab, where we do the entire MLOps, which includes EDA, visualization, model training, evaluation, and the prediction. So the very first step is we have all the libraries installed in place for our system. We set up the AWS environment, provide access key, secret key, and then, as I mentioned earlier, since we are reading the data in a distributed manner, we use Dask, which acts as a distributed library for Python. And Dask does what it does is it creates different partitions internally and then finally creates a single pandas data frame, so it's faster and efficient way to read a larger data set. Here we define the training part where we are actually taking the data, then we read the CSV, but with the Dask instance where we define access keys and secret key parameters. As you can see here. So this is how the first 5 rows of the data look like for our training data. This is the number of the rows and the columns that we have initially, which is obvious too much. That's why it's not able to display a proper accurate number. And this is the data types, this one, and these are the data types that we have for each one of them. Now let's start our EDA. So the first thing that we do is clean the pickup date time variable. We draw all the NA values here, then we check the shape again, then we change that data type to date time for the pickup date, and then we segregate individual input features for columns like year, month, week, hour, minute, so that it's easier for our analysis. Then we check the data type condition. We keep certain observations in mind, like the passenger count, as you can see here, should not exceed 6, even if we consider SUV. And latitudes range from -90 to 90, longitudes range from -180 to 180, and few missing values and high values of the fare and passenger count are present, so we also decided to remove them. So now, based on the definition, let's first describe the passenger count column. So this is the passenger count column. This is actually not possible, right? So we drop all of the rows where the passenger count is greater than 6. So this is just a command for that, and we also remove all the ones where the passenger count is 0 here. Then again describe the passenger count column. If we remove the passenger count, then the next is we sort, then we do cleaning. Let's move on to the fare amount variable. Let's first sort the fare amount. So we kind of sort the data ending in the fare amount, and then we count the rows where the fare amount is lesser than 0, and then we drop the fare amount which is lesser than 0 since we are getting the count, and then we check the minimum value which is 0, which is fine. Sometimes it can happen that the passenger might start the trip and then end the trip when the fare amount becomes 0, right? So that's one scenario. But we want to remove the fare amount lesser than 1, and since the New York City fare system is built within the city, we take the maximum price to be around $454. So we drop all the fare amounts which is greater than $455. Then, as I mentioned, that we need to remove the values of the latitude lesser than minus 90 and latitude greater than 90. So we remove those ones for the proper coordinates. Then we drop similarly for the longitude, that is lesser than minus 180 but greater than 180. Then we again describe the shape, and there is no null values. This is another data mining technique that we use, which is called as Haversine formula. Let me come to that point here. Here. Haversine formula. To calculate the distance between the coordinates, so we take the coordinates which is pick up longitude, pick up latitude, drop off longitude, drop off latitude, and then apply the Haversine formula to this, and then calculate the distance here in kilometers, and then we append the distance to our training data, as you can see here in this column. Now we sort the distance, see what kind of distance we have after calculating, and then we do the cleaning for that. So we drop the distance which is 0, and we include only the distance which is not 0, right here. Since we see that the lot of distance is created in 130, so we drop all of those values whose distance is created in 130 kilometers, which obviously doesn't make any sense. Now after we apply the Haversine formula, then we also split the pickup date time variable into different variables, like here you can see, like month, year, day, etc. So we don't need to have that pickup date variable now, so we can drop that too. And we also create a distance, so we'll not need to mention the coordinates. We can just use the distance as the final column. So now our CSV columns have the fare amount here, as you can see here. One second. Here are the final columns, like fare amount, passenger count, year, month, date, day, hour, distance. So once this is done, then we need to do the type conversions for all of this here. Basically convert everything into float and integers, and remove any object data type. Once we have done this initial screening and all the initial cleaning part, we move on to the data visualization part. So we mainly do the visualization of these parameters, that is the number of passengers, pickup, date, time, day of the week, and the distance. So these are the four main features. Let's see. So let's first see the passenger count versus the passenger count by graph. Uh, Here, let's find out the relationship between the number of passengers and the fare. So uh, here, so this is the number of the passengers, and this is the fare, as you can see. So we can see that the single traveling passengers are the most common. So we see when the passenger count is 1, the fare is maximum, and at the same time we can also conclude that the highest fare is coming from the single and the double traveling passengers. So 1 and 2 are obviously the most. Now the second thing is the here are at what time of the day the prices are higher. So let's then calculate the distance between the hour and the relationship between time and fare. So we see that the lowest gap is at 5 a.m. in the morning, and the highest is at, let's say, see here, 7 p.m. in the evening. And it also makes sense because 7 p.m. is usually like a rush hour, and 5 a.m. is actually when people start getting ready. So that has to be the lowest, right? Now let's just talk about the distance and the fare. Yes, but we can also conclude some things like for the day, the highest fare seems to be on Sunday and Thursday, and the lowest on the Wednesday and Monday. Maybe due to low demand on the cabs on Saturday, the cab fare is low, and high demand for the cabs on Sunday and Monday. So this is a high fare curve. Now let's then calculate the relationship between the distance and the fare. So it's kind of a linear curve here, as you can see. Now let's move on to the feature scaling part, where we, one second, yeah, where we kind of check if the training data is normally distributed or not. So for that we basically use Seaborn to actually visualize the plot. So this is the distribution of the variable fare amount, and this is the distribution of the variable distance. So we see that it is obviously not uniformly distributed. But in order to reduce the skewness and make it more normal, we apply log transformation. So after applying log transformation in order to reduce the skewness, we then again see whether if it's normally distributed or not now. So one second. And we see that it is better than before, and the skewness has obviously reduced. So this is the distribution of the fare amount and the distribution of the variable distance, as you can see here and here. So finally we have our continuous variables as normally distributed, and we don't need any further feature scaling technique. Now once we have the normally distributed fare, we then are ready for applying ML algorithms. Here, yeah, so now before we actually build our ML models, we want to make sure that we split the training data into split and test data, with keeping in mind that the test data is 20% and the training data is 80%. Once we have split the data into training and testing data, the very first model that we build is a linear regression model. So we basically build a linear regression model, and then we do the prediction on the trained data. So once we have done the prediction on the training data and test data, like the X train and X test on linear regression model, we evaluate the model further. So we take the two performance metrics into consideration. The first one is the root mean square error and R square error, as you can see. So basically RMSE value of the testing data is 0.25, and the training data is 0.25 as well. So basically it's 0.25. Then the R square value is here for the testing data is 0.77. Then we move on to the second model similarly, which is decision tree regression. So similarly, we build a model against X train and X test and do the prediction, and then we calculate the root mean square error and R square. Score the RMSE value for this one, for this test data is 0.29, as you could see here. Yeah, and for R square it's like. Then we check the random forest model. Similarly, for a random forest model, the RMSE is 0.23 and R square value is 0.81. Then we also do gradient boosting regression, which is actually chosen as an improvement over random forest. So in gradient boosting, we build a model and again calculate RMSE value and R square. Score, we see that RMSE score here is so this is the R square score, that is 0.79, and RMSE is 0.24. So we see that we were expecting a better R square score for gradient boosting than random forest, because random forest R square value was kind of higher. So in order to actually improve our model, we can optimize the results with hyperparameter tuning. So we tune the model with hyperparameters using a random sort CV here. We define the configurations such as n estimators and max step, and then we initialize the random sort CV with less number of iterations and CV folds. We then fit the model on the training data, and we can predict the model on the test X data, and then again calculate the performance matrix. We see that the RMSE value is 0.23 and R square value is 0.82 here, which is clearly now greater than that of the random forest. So we can say that the tuning of the hyperparameters actually worked. So what we have done is we have basically, like, just summarizing, we have actually used different ML models, but we have also, in order to improvise the results, we have used random forest regressor with random sort CV to actually optimize the results further and then evaluate the model again. So finally what we are left with is we need to basically predict the fare from the provided test data. So after applying all the models and before actually predicting the fare, we need to select the best model which basically has the best performance. So in order to do that, we actually compare the performance matrix of all the models, which is linear regression, decision tree, random forest, gradient boosting, and then finally random forest regressor with random sort CV, where we have optimized the results further. So then we basically define the best model as random sort CV on the random forest regressor, because we know that the random sort CV, the random forest regressor, has the highest R square value and the lowest RMSE value. Yeah. So first we define the test data, where we are actually collecting the test data in order to make a prediction. So this is how the test data looks like, and then we again perform the outlier detection, do missing value analysis for the initial test data, like how we did for the training data initially, and then finally what we do is use random sort CV model to actually predict the fare, as you can see here. And once we do that, we then attach the predicted fare amount to the test data column, and then once we have predicted fare amount appended to the test data here, we save it as CSV and send it back to the clean data S3 bucket, which I showed you earlier. I can show that again here. And this is how the clean S3 bucket looks like, as you can see here, where we have stored the final CSV file, which is the predicted fare amount in CSV format here. So this is our end-to-end big data pipeline, right from the data collection part to data storage to data cleaning, and then performing the complete ML operations, MLOps, where we do further cleaning, exploratory data analysis, visualization, and finally model training, evaluation, and prediction. So, thanks a lot.